All right, welcome to Math341, Lecture 16. So today the goal is to do differentiating identities. This is one of my favorite techniques in the course. And the purpose of this, let me just save some power and kill the projector, is to find a way to calculate expected values in moments quickly and cleanly and easily. We saw the binomial distribution, and we saw the horror of having to do the sum of k times the probability, or k squared times the probability, to calculate the mean and the variance. I'm going to show you a trick that will allow you to get a lot of these very easily. All right, and so let's start off with the geometric series. So we proved the geometric series formula early in the semester by imagining a game of basketball between Bird and Magic. Did we do the algebra proof as well, or did we just do the basketball proof? All right, so let's do it really fast. So let's let Sn be 1 plus r squared all the way to r to the n. Let r times Sn be just r plus r squared plus r to the n plus r to the n plus 1. And so when you look at this, it should scream subtract, that all the intermediate terms will cancel. This should remind you of telescoping sums, which you might have seen in calculus when you prove the fundamental thing of calculus. So when we subtract, we get 1 minus r times Sn is 1 minus r to the n plus 1. So we get Sn is 1 over 1 minus r to the n plus 1 over 1 minus r. And I'm choosing to write it this way because if I write it this way, you can see this is what it's going to in the limit, and this is the little correction, at least so long as the absolute value of r is less than 1. So if the absolute value of r is less than 1, then Sn is going to converge to 1 over 1 minus r. And this is the geometric series formula. All right. We can use this to define a geometric random variable. Okay. So for a geometric random variable, I need to have non-negative probabilities. It's going to add up to 1, and it's going to be defined discretely. So a lot of times the way people do this is they do it, how many tosses do you need before you get ahead? Unfortunately, what you will see is depending on which book you use, there can be a slight difference as to are you defining the probability to be p or 1 minus p for the success. It's how many failures do you need before you get the first success, or at what location is the first success. They're extremely similar problems. So we will say the probability that x equals n is going to be 1 minus p to the n. And this will count the number of number of failures before the first success. So if n equals 0, with 1 minus p equal the probability of a failure. No, 1 minus p is the probability of success. And p is the probability we fail. So what's the probability we have a success on our first toss? It's going to be 1 minus p. What's the probability we have our first success on the second toss? We fail p, and then we get a success, 1 minus p. So note, the sum n goes from 0 to infinity of 1 minus p times p to the n is just 1 minus p times the sum n goes from 0 to infinity of p to the n. So it's 1 minus p, 1 over 1 minus p So this is a random variable, right? I'm just defining 1 minus p as the probability of success. I don't like this, but it counts the number of failures you have before you finally get a success. What's the smallest number of failures you could have? 0, right? You cannot have negative numbers of failures. And then you can have any integer number of failures. So here, n is going to be in 0, 1, 2, 3. You always want to have a sense of where is your random variable defined. So the first thing we want to do now is, what do we want to ask about this distribution? Mean. So the mean, well, it's the expected value of x. So it's going to be the sum, n goes from 0 to infinity, of n times 1 minus p times p to the n. So it's 1 minus p times the sum, n goes from 0 to infinity, of n p to the n. When you see an n p to the n, what does this kind of look like? Yeah.
Something to do with the product rule. Not product rule, whatever the hell you call the rule when you bring down
The derivative.
Yeah.
The derivative of just a nice polynomial.
Polynomial rule.
So this is equal to p d by dp of p to the n. And the reason is, if I take the derivative of p to the n, I'll get n p to the n minus 1. And then if I multiply by p, I get back to where I started. I have an infinite sum and I have a derivative. What do you think I want to do? Yes? Nope. I have a derivative followed by a sum. What do you think I want to do? I'm sorry? Yeah, take the derivative of the sum. I want to switch the orders. If I have a finite derivative, if I have a finite sum and a derivative, I can interchange a finite sum and a derivative. The difficulty is when you have an infinite sum. So we talked earlier in the semester that you have not proven in a calculus class that you can interchange an infinite sum and a derivative. It's debatable with some of you whether or not your teachers even proved you can do this if you have a finite sum. Almost surely they did it if you had a sum of 2 functions. And then we saw how you could group things with parentheses and get any finite number. But to get an infinite one, that's not always true. So this leads to the subject called differentiating identities. And this is one of my favorite techniques in all of mathematics. Identities are the bread and butter of the subject. You do a lot of work to prove an identity. I feel like I'm now on the Home Shopping Network. Imagine you have this identity, I can give you infinitely many more identities from it. And the first 100 mathematicians to master this will get a pair of Ginsu knives or something like that. Yeah. This sounds like something too good to be true. You have this box that's going to generate new identity for you. Identity after identity after identity after identity. And the idea is roughly the following. You have some function with some different types of parameters, maybe x and alpha. And you have some kind of expression depending on x and alpha. And then you apply d by d alpha. Oh, actually, this should be partials. Partial with respect to alpha to both sides. And the idea is, if you can calculate both sides independently, they must still be equal. And this allows you to generate new identities from old identities. So rather than proving the theorem in full generality, let's just show how to apply this to a huge collection of problems. So for example, let's say we have f of x is going to be the sum, n goes from 0 to infinity, of x to the n. Did we do the generating function for the Fibonacci numbers? We did that, right? And we saw that we could often bundle local information and get this nice global object. What is the sum of x to the n? This is equal to what? We just did this a few moments ago. 1 over 1 minus x. So this is a really nice expression. I can differentiate this with respect to x without any trouble. So we're going to apply the operator x d by dx. And the reason we apply x d by dx is it keeps the power of x the same afterwards. And so we get x d by dx of the sum, n goes from 0 to infinity, of x to the n. And now when I take the derivative of this, when the dust settles, I get x over 1 minus x squared. Through the algebra. I'm just going to write that. Okay? So you take the derivative and multiply by x, you get the following. Well, now I'm going to flip the derivative in the sum. And so I'll get x times the sum. I'm sorry. I'll bring this all inside and go n 0 to infinity. And when I take this inside, I'll get n x to the n is equal to x over 1 minus x squared. Yes?
Why can we flip the sum and the derivative here?
So, what class?
Analysis.
Be more specific.
Real
Real analysis would justify that. Complex analysis would also justify that with an infinite series as to when can you do this if you're within the radius of convergence. Now, it turns out for the geometric series, I can actually prove this is valid, and I will do so in a minute. Whenever you have an infinity, you must be careful. And as a rule of thumb, whenever I say we must be careful, this always means we need real analysis. Yeah. This is the class that allows you to do all this stuff. Last time I checked, this class was numbered less than 350. So real analysis is not a prerequisite for this class. One of the purposes of this class is to motivate you to take a class like real analysis, where you can see the justification for doing stuff like this. Okay? Right now, I am wearing my engineering hat, and I am not worrying about is this justified or not. I'm just formally computing and seeing what we get. And now, notice we can calculate the mean of the geometric random variable. So for instance, if we now look at what we go over here, the mean was 1 minus p 1 minus p times n p to the n. So we take x equals p, multiply by 1 minus p, and we get 1 minus p times the sum, and it goes from 0 to infinity of n q to the n, is equal to 1 minus p. Now x is equal to p, so we get p over 1 minus p squared, which is equal to p over 1 minus p. So this is the mean of a geometric random variable. I'm going to just move this so that both parts are in focus. The mean of a geometric random variable where you have probability 1 minus p of failure. What's the easiest case to analyze? Zero. So if p equals 0, what's your probability of success? 100%. What is the mean number of tosses to get a success, given that you always get a success? 1 toss. So always check extreme cases. If p equals 1, you get a mean of 1. What's another extreme case? 0. If you get p equals 0, did I do this wrong?
P equals 1.
Sorry. I'm sorry. We want p equals 1 for always getting a success. This is why I hate this notation. It's from the makers of cosecant, goes with sine, comes 1 minus p, goes with the probability of a success. So if p is 0, then we always have a success, so we have a mean of 1. If p is 1, we never have a success. You get a mean of infinity. That seems reasonable. What's another good choice to take for p? A half. And this would get you a mean of 1. Oh, wait, so what is the first one? Oh, sorry, the first one is 0. I'm sorry. The first one is 0 because we're counting the number of failures, right? I hate this. The first is 0 because we're counting the number of failures. How many failures should you have if you always get a success? You should have no failures before your first success. I much prefer to think, what is the location of my first success? The location of my first success is 1, and my hand just has memory of this and is writing 1. All right, if p equals 1/2, we get a mean of 1. That seems to make sense. You know, half the time we get a success immediately, so there's no failure. A quarter of the time we get a first success on the second, an eighth, etc. That seems reasonable. And then you can look and see what happens if p is greater than 1/2. If p is greater than 1/2, then your probability of success is small. Well, if p is greater than 1/2, so let's look at what would happen. So let's say p is 3/4. So your probability of failure is pretty high. And then you would get a number here that's much larger than 1. So if p equals 3/4, this would lead to 3/4 over 1/4, which would lead to a mean of 3. And we can see the mean is increasing as the probability of success decreases. That's really good. Yep. The less chance you have of a success, the longer it should take before you get the first success, the more failures you should have.
I had a question about this. You said multiply by 1 minus p. Is that because we went through the differentiating identities and then because we wanted
No, it's because we know that the formula for the mean has a 1 minus p.
Right, so we did this first.
We did this first, and then to apply this for the geometric random variable, we needed a 1 minus p.
Right, so it could have been 10 different things.
Correct.
Okay.
Correct. If we wanted to calculate the variance, how would we calculate the variance? So for the variance, we want the expected value of x squared minus the expected value of x squared. Remember, we have two formulas for variance. We also had this equals the expected value of x minus mu squared. We don't want to use that. We've already computed the mean, and this is a pure sum to calculate. This is an easier one to calculate. So we want to calculate now the sum of n squared. So we would calculate the expected value of x squared would be the sum, n goes from 0 to infinity, of n squared 1 minus p to the n. So this would be 1 minus p, the sum n goes from 0 to infinity, of n squared p to the n. So this would be 1 minus p times p d by dp acting on p d by dp of the sum n goes from 0 to infinity of p to the n. We differentiate once, we get n p to the n minus 1 times p is n p to the n. Differentiate again, we get n squared. And now we can just plug in, this is 1 minus p d by dp times p d by dp of 1 over 1 minus p. I think it's an extra parenthesis. And so now this is just a calculus problem. Take the derivative of this, multiply by p, take the derivative of that, multiply by p. And that's your second moment. So it's just a sequence of derivatives. If you go to Mathematica, Mathematica can take derivatives of these functions very easily. By all means, when you're doing homework problems, check your work on something like Mathematica. Make sure you haven't made a mistake. So we can calculate the third moment, the fourth moment, the fifth moment very nicely. The thing that's a little bit annoying is the derivatives here. We have to keep putting these p's. So how many of you ever heard of the phrase Tanstoffel? Anybody know the phrase Tanstoffel? One place where it's used frequently is Heinlein's book, The Moon is a Harsh Mistress. All right. There ain't no such thing as a free lunch. You pay for everything in life. If I do p d by dp, this makes the algebra very easy on this side. The pain is now when I keep taking the derivatives here, it's making it worse because now when the derivative hits, it's like the Leibniz rule, if you remember that. the d by dp can hit the p, and the d by dp can hit the derivative of that. And you have all these cross terms for derivatives. So much of life is trying to decide where do you want to buckle down and take the algebra hit. We can take the algebra hit over here and differentiate a worse function, or we could take the algebra hit here and instead of doing p d by dp, just do d by dp. And if we did that, we could study instead the sum of n minus 1 p to the n minus 2. And if you wanted to, that would just be apply d by dp twice. So we could do that. And then multiply by 1 minus p times p squared. And then that would give us 1 minus p times the sum, and it goes from 0 to infinity, of n squared minus n times p to the n. And this would be the expected value of x squared minus the expected value of x. Because the n squared will give us the second moment, and the n will give us the first moment. And this would now have a much easier thing to differentiate. This would just be d squared by dp squared of 1 over 1 minus p. So again, I strongly urge you to read the book or just go through this yourself slowly, put in all the steps, put in all the arguments to justify this. The differentiation here is much nicer. At a cost now, at the end of the day, I don't get the second moment, I get the second moment minus the first. That's fine, I know what the first is. So in terms of doing the algebra, I might actually even prefer doing this, because I already calculated the mean. So adding back the mean to me is not a big deal. Whereas, calculating the derivative here, well, if I'm using Mathematica, I'm not doing the differentiation. So in that case, I don't really care. This is a fine derivative to do. So again, the whole thing to worry about is where are you taking the algebra hit. But what I hope you're beginning to see is this is a powerful method. All right. As I am not going to prove all of real analysis in this class, we will not justify rigorously why all of this works. But for the geometric series, we can actually justify this, because the geometric series has a truly wonderful property. So what happens if you throw away the first million terms of a geometric series? What's left? Another geometric series. Right? Remember to email me when you make comments in class. If you throw away finally many terms of a geometric series, you get a geometric series. So I can write the sum, n goes from 0 to infinity of x to the n. Let's sum this, n goes from 0 to big N of x to the n, plus the sum, n goes from n plus 1 to infinity of x to the n. This is the sum, n goes from 0 to n of x to the n, plus x to the n plus 1, the sum, say, m goes from 0 to infinity of x to the n. What does that sum equal? So I've just got a full geometric series starting at 0. What will this sum equal? I'm sorry? No, just the sum, just this part right here. It's a geometric series with ratio x. We'll assume x is less than 1. Yeah, 1 over 1 minus x. So this is going to be the sum, n goes from 0 to n of x to the n, plus x to the n plus 1, we'll say divided by 1 minus x. And now, if we apply d by dx, we'll get a sum, n goes from 0 to n, we'll apply x to by dx, of n x to the n. And now what do we get to use to take the derivative of this? We get to use the quotient rule, right? So we get x, or 1 minus x squared. We get the derivative of this, we get n plus 1 x to the n minus x to the n plus 1, and the derivative of this will just be negative 1, so that reinforces. And now, as long as the absolute value of x is strictly less than 1, even though the n is growing, each term here has at least an x to the n, and this is going to be exponentially small. So if we take the limit as n goes to infinity with the absolute value of x less than 1, this part's going to go to 0, and this part will go to your infinite sum. So this is at least the proof in the case of the geometric series, or really close to the proof, that you can justify switching the order of the sum and the derivative. There is, of course, a situation where it's very easy to justify switching a sum and derivative. What kind of sum can we always switch with a derivative? Yes? A finite sum. So if there's a finite sum, I don't have to worry about justifying anything. A finite sum, I can always switch the orders. How many of you have seen this method before, out of curiosity? Okay. So this is one of my favorite ways to calculate moments of probability distributions. So there's a lot of orders we can do things. Let's do the binomial random variable next, just to justify my excitement here, and just show you that it takes that painful problem and makes it trivial. Right? The challenge is always finding an identity. That's the hard work. Once you have the identity, then you can apply the method. Sometimes there's a little bit of an art in terms of how do you do the algebra. This is the Tanstaffel. Along these lines, I would like you to find the roots of the following. I will give you the polynomial x squared minus 7x plus 12. What are the roots? Yes. -3 and -4. Yes. Well, no.
No.
3 and 4. So x minus 3, x minus 4. And you did this by using the quadratic formula doing negative? No, okay. You just looked at it and you saw. For a lot of polynomials, that's what you do first. You quickly look at it and see, can I sniff out the roots? Imagine I'm feeling less generous, and I give you this. Can you find the roots? Yeah, you go to the quadratic formula. It's a mechanical approach. It will work. It's slower. If you can just see the roots, this is the divine inspiration method. Just write them down. The problem is solved. If you can't see this, we at least have a mechanical way to do this. For differentiating identities, you need an identity to start with. Most of the time, it's going to be clear what that identity is. It's got to come from the fact that it's a probability distribution. What's the two pieces of information you know about a probability distribution? Non-negative, and integrates your sums to 1. So it's essentially going to come from the fact that the sum of the integral is 1. That's going to be your identity. So you might need to move a parameter over to the other side. Sometimes you have to do a little bit of work to figure out exactly what it is. So let's do a binomial random variable. So we'll say x is binomial NP. So the probability that x equals k is going to be n choose k, p to the k, 1 minus p to the n minus k, and k will be in 0, 1, 2, all the way to n. So we know that the sum k goes from 0 to n of n choose k, p to the k, 1 minus p to the n minus k equals 1. I can try to apply d by dp or pd by dp, but the problem is, well, I'll bring down a k when it hits this, I'm going to bring down an n minus k when it hits that. I only want the derivative to hit part of it. Am I allowed to have the derivative hit just part of it? If I have the derivative of a product, can I say, oh, I'm going to just take the derivative of the first part and just not? No. So here's the trick. We study, instead, the sum k goes from 0 to n of n choose k, p to the k, cubed to the n minus k. And by the binomial theorem, what is this equal? So this is one of the things you need to remember. What does the binomial theorem say the sum equals?
This P plus K.
Not P plus K, P plus Q.
P plus Q. To some power.
Yes, which power? There's only one power it can be when you look at it. Yeah, it has to be to the nth power. And then when you expand it out, you get a P to the n, and then a P to the n minus 1 Q with a coefficient of n choose 1, and so on and so on and so on. In your mind, what should you be thinking Q equals? So in your mind, what are you thinking Q equals? 1 minus P. But at this point in life, I'm not letting Q equal 1 minus P. I'm introducing Q as a separate variable. Later, we'll take Q to be 1 minus P. But not now. Because if I have Q as a separate variable, if I take the derivative with respect to P, it's not going to hit anything here. So now if I apply P d by dP, I'll get the sum, K goes from 0 to n, of K, n choose K, P to the K, Q to the n minus K. And over here, when I take P d by dP, I'll get a n P plus Q to the n minus 1. Now, we take Q equals 1 minus P, and this will give us the expected value of x is just equal to n times P, because this expression is now 1. And that finishes the algebra. The algebra is not that bad. This is the hard part, right here. That's where you have to think. Because if you try to look at this directly, you're going to get K coming down and n minus K coming down, and it's going to be a pain. But if you start off with the binomial theorem, and that's really what we used to get this. We really used the binomial theorem, and then we substituted 1 minus P into the binomial theorem. So I'm just trying to remember where this came from. And if we do that, it's not so bad. So this is how to calculate the mean. If I want to calculate the variance, I would just apply P d by dP again. This is not a painful function to differentiate again. I'd have to use the product rule, but not a big deal. As an aside, I will show you a way to bypass the product rule if you don't want to use the product rule. So we have n, P, P plus Q. I can write this as n, P plus Q minus Q, to the n minus 1, times P plus Q to the n minus 1. So this is going to be n, P plus Q, P plus Q to the n minus 1, minus nq, P plus Q to the n minus 1. So this is going to be n, P plus Q to the n, minus nq, P plus Q to the n minus 1. It doesn't really matter how you do this, but this is a really nice trick of adding 0 to sometimes simplify some of the algebra. And now I don't have to use the product rule. Each term is going to be very easy to differentiate with respect to P, because I've now got the Q floating outside. All right. This is the binomial random variable. Any questions on the binomial random variable? Okay. Next random variable to look at is the exponential random variable. How many of you have done an exponential random variable in another class? Okay. How do you define the exponential random variable? There are two definitions. So how do you define it?
You just have its PDF be e to the lambda times e to the minus lambda.
Okay, so one possibility is the density function is lambda e to the what?
Minus lambda. Or minus lambda x.
That's one definition. Does anybody know another definition of the exponential? Okay, but how would you phrase it? So the other way of doing it is 1 over lambda e to the negative x over lambda. These are two equivalent definitions. So for those of you who've taken stats before, they use this one. Okay, I don't like this one. The reason I don't like this one is, what is the interpretation of lambda in this? Well, it's a constant, but it's your parameter for the distribution. What's the interpretation? In this one, lambda, I believe, is the mean. In this one, lambda is the reciprocal of the mean. I would much rather have my parameter be the mean than the reciprocal of the mean. Is there much of a difference between, let's use a different letter. Let's use the letter omega here. What's the relationship between omega and lambda? Yeah, omega is 1 over lambda. So if you're comfortable using one formulation, you can always convert to the other one by just replacing all of your lambdas with 1 over omegas, or all your omegas with 1 over lambdas. It's just a question of, what do you want to define as your parameter? Do you want your parameter to be the mean or the reciprocal of the mean? I much prefer having my parameter be the mean. This is the advantage of being the professor. I will use this one. We need an identity. So we know the integral from 0 to infinity of 1 over lambda e to the negative x over lambda dx equals 1. So my identity is the integral from 0 to infinity of e to the negative x over lambda dx equals lambda. So there's my identity. Okay? Now, let's apply d by d lambda. And I think I know where things are going. I'm going to apply lambda d by d lambda. If you didn't apply lambda d by d lambda, if you just applied d by d lambda, wouldn't be a big deal. If you want, maybe I should write it as lambda partial with respect to lambda, to just remind myself that we do still have that variable x in play. I need to justify the derivative of the integral as the integral of the derivative. What class do we use for that? What class will justify the interchange? Real analysis. If you do not want to justify these interchanges, what department can you move to?
Stats.
Yeah, probably. Although they are, at least, we are still temporarily one big happy family. Yes?
Physics?
You can move to physics. What else? If you want to go even farther away. Well, I mean, yes, but econ, yeah, also fine. But if you're doing the subjects well, you will justify this. Physicists and economists, if they do a good job, they have a natural intuition of when can you do this stuff. You're like, if you look at Feynman, a lot of his stuff, it's really hard to justify his calculations, but he has incredible physical intuition as to what should work. And then later in life, people have made it work. I showed you, I think, solving the integral of f minus 1 equals, right? We did that problem, and you got the exponential function. You can make some of this stuff rigorous. Good physicists know how to play fast and loose with the math. So if we apply lambda d by d lambda to both sides, we would get the integral from 0 to infinity of lambda d by d lambda of e to the negative x over lambda dx equals lambda d by d lambda of lambda. Oh, that's a fun derivative to do. What's nice about this is, when I take the partial with respect to lambda, an x is going to come down. So when I take the derivative, I will get the integral from 0 to infinity. I'll get lambda. Then I take the derivative of this. So I'll get a negative x over, I've got lambda to the negative 1, so that'll be negative lambda to the negative 2. So the minus signs reinforce. I get e to the negative x over lambda equals lambda. And then this is the same as x times 1 over lambda e to the negative x over lambda dx equals lambda. And this is just, by definition, the expected value of x. So we're able to get the expected value of x without any trouble. If you wanted to calculate the variance, we would just apply lambda d by d lambda again, and another x would come down. So what you might do is you might start with this expression here, x 1 over lambda equals lambda. I might pull the lambda over to the other side. So let's just do that calculation. What's nice is at the end of the day, you want a 1 over lambda e to the negative x over lambda, because that's your PDF. So we want, when the dust settles, to be left with that. So we have the integral from 0 to infinity of x e to the negative x over lambda dx is lambda squared. I just brought the lambda over to the other side. All right? We apply lambda d by d lambda. And so when we apply that here, we get a lambda, an x, and then when we take the partial here, we get an x over lambda squared just as before. E to the negative x over lambda dx. And now we take lambda times the derivative of lambda squared. So that will just be 2 lambda squared. And we apply lambda d by d lambda to lambda squared. All right? So now we get the integral of x squared, 1 over lambda, e to the negative x over lambda dx is 2 lambda squared. Life is good. That's exactly what we need for the second moment. And again, if you didn't note to apply the lambda here, you would just have to then multiply by 1 over lambda to get the PDF. We want to get the PDF here. So now the variance is going to be the expected value of x squared minus the expected value of x squared. The expected value of x squared is 2 lambda squared. The mean is lambda. So we get lambda squared. So we get the standard deviation is what? The standard deviation is what? I couldn't hear you.
Lambda?
It's just lambda. So lambda is actually both the mean and the standard deviation for the exponential random variable. If you think about it, is it reasonable that the standard deviation is not lambda squared? So again, you are going to do a lot of algebra in your life. I want you to be able to look at the result and ask, is this reasonable? Am I shocked by this answer? Are you shocked that this has the same units as the mean? No. We measure the mean and we measure the standard deviation in the same units. Think of x as being measured in meters. When I have an exponential, I've got to have a unitless quantity here. E to the u is 1 plus u squared over 2 factorial plus blah, blah, blah. U must be unitless. So if x is in meters, lambda must be in meters as well. This is why I like to use this as my definition of the exponential, because x and lambda now have the same units. It's got to be unitless. So if the mean has units of meters, so does the variance. So the variance has to be able to form lambda. It can't be something like lambda squared or square root of lambda. And if you can do simple calculations like this, you can often get a really good sense of what the answer is before you do the calculation. There's a lot more problems we can do. Rather than doing another one of these problems, I'll just give you a simple dimensional analysis argument right now, and I'll end the class with that. How many of you have taken physics labs? In high school even. All right. So let's imagine you want to calculate the period of a simple pendulum. So we've got the pendulum bob swinging back and forth. Right? This is not to get me steps. We're talking about pendulums. What is the unit for the period? Seconds. So if you imagine the problem, here's a pendulum bob. It's swinging. Here's the initial angle. Here's the length in meters. The mass in kilograms. We have the acceleration due to gravity in meters per second squared. The angle is in radians. And the period is in seconds. I need to somehow combine these units in such a way as to get seconds. What can you immediately tell me has no impact on the problem? Mass. There's nothing to cancel the kilograms. So I've got the radians, which is unitless, and I've got the meters and meters per second. What's the only way to get seconds? It's got to be square root of L over G. If I do meters divided by meters per second squared, that's seconds squared. The square root is then seconds. So it's got to be some function of theta times the square root of L over G. So before you even go to the lab, you know that if you quadruple the length, you double the period. If you could somehow have or take with the 1/4 of the acceleration due to gravity, if you could somehow change the gravitational constant, you know how that would. Now, one of these is easier for us to do than the other. I will risk saying this even though I know the answer is no, but this way I can at least talk to my Star Trek friends later. Any Star Trek fans here? Anybody ever watch Next Generation? There's a character Q who is essentially a god, and there's an episode where the other gods are upset about him being such an asshole, and so they decide to make him mortal. And because he's pissed off so many species, he runs to humanity for protection. And there's a catastrophe that's about to happen to a planet. It's going to be hit by a giant asteroid. And they're trying to figure out how to save the planet. And Q just goes, well, okay, your attractive beam isn't strong enough. We'll just change the gravitational constant of the universe, and then it'll be more powerful. We can't do that. Oh, well, then you're out of luck. And then, of course, they find some technobabble way to change the constant of gravity locally, and everything is fine. We can't change this that well. But we can change L very easily. And if we know that there's a proportionality constant, we could keep theta fixed, change L, and get some sense of what's going on. It turns out that this is, I believe, independent of theta, at least if theta is small, and is essentially 2 pi, if memory serves. If not, it's 1 over 2 pi if I'm doing things the wrong way. You're never going to detect something like 2 pi with an argument like this. But the fact that you can just quickly look at this and see that the functional dependence is L over G, that's one of the things I want you to get out of this class. When you have a new problem, how can you get a sense of what the answer should be before you actually do it? I've already written the midterm and the final for this class. I don't remember what's on it. I believe there's one problem, I think, where I ask you, before you do the calculation, what do you expect the answer to be? When you're taking the exam, of course, I don't know the order in which you do the problems. Right? I strongly urge you, though, to think about the problems before you do them and try to get some sense of the answer. Or if not, once you have the answer, go back and ask, is this reasonable? So I've applied the method of differentiating identities to geometric random variables, to binomial random variables, to exponential random variables. You can do this to a large class of random variables. You will have some for homework problems. You can do it for the normal distribution. You can use this to calculate the moments of the normal. It is an incredibly powerful method. Okay, so I'm going to stop here.